Okay, so this is number 2 and calculating equilibrium constant, and then how to calculate the concentration of the compounds, reactant or products. So let's read the problem. The constant Kc is given, and the key information is this constant is Kc, concentration-based equilibrium constant. The value is really large. That means that they favor the formation of the product. So this is an HCO2H, which is a acid, and this is called a formic acid. And formic acid is decomposed into CO, carbon monoxide, and then the water. And then the question is, if the 0.2 moles of formic acid placed in a vessel, and then that's 1 liter vessel. So I guess concentration HCO2H is provided to you, which is a 0.2 mole per volume, 1 liter, right? So therefore, your answer is this is a 0.2 molar. So that's initial concentration. And what will be the concentration of? So this is, let me switch the color. The main question is they're asking the concentration of CO and then water when the system reached the equilibrium. And the bigger information is hint. Where does the position of equilibrium lies when K is very large? I mean, just to answer this hint question is they favor product. Heavily, right? So heavily favor the products. And then, this is an equilibrium constant problem, so we have to construct the logic, ICE equation built around the chemical equilibrium reaction. So HCO2H, formic acid decomposed into CO, carbon monoxide, and then H2O. Okay, I don't know what my tablet is doing here. H2O. And then they go back and forth, and that's going to do. So let's figure out the initial condition here. And the initial condition is, okay, 0.2 molar concentration of formic acid, and you do not form anything here. Okay, and then I want to do the change. The change is, which is, okay, I'm going to lose some because there is nothing product form. So equilibrium will produce the products, and they will generate X, and then they will generate X. Okay, so this is a consideration, and then what you find out here, this is a moment that you need to make a stop and to think about the meaning of what this X means. Okay. Well, usually the approximation, the X, I want it to be very small values. So X, I want it to be small. But here, it is not small here, right? Because the Kc value is really large. This is almost close. This value is almost close to 0.2. So I am going to re-establish the new initial condition, which is, let me just suppose that X is, for now, 0.2 molar. So this is using the fact that the position, when K is really large, heavily favors. So I'm just going to make another case so that I can have an easier way to solve this problem. So I'm going to assume that first, let me just okay, so this is an equilibrium, your starting point, this is initial condition. Equilibrium almost favor the product, and then you're going to back out a little bit. So this is my idea, okay, 0.2 molar is completely consumed, then you can back generate certain amount. So this is how I'm going to do. So initially, I am going to say everything is used up, and by doing so, you will have 0.2 molar. 0.2 molar is being generated. So this is based on this Kc is being large, this is my new initial condition. Once you have this, the calculation, follow-up calculation easy, because and the change for this new initial condition now, because something has been generated, so this is you're going to lose some, you're going to lose some, you're going to generate some. And the beauty of this new establishment of the new initial condition is x is really going to be very small numbers. When x is very small, we can use various approximation, and you can see what can be done. So, quote unquote approximation, and I will show you what approximation I'm allowed to do. So I'm going to add it up, and so this is an equilibrium finally, and that's the concentration of x, and the 0.2 minus x, 0.2 minus x. That's a concentration. Okay, so this is I kind of draw this kind of strange diagram. So this is your starting point, but you have a new initial condition that let's suppose everything is generated into the product to 100% conversion, and then you kind of think about shifting the equilibrium back to generating a small amount of the reactant. So that's the kind of the idea. Yep. At any rate, that this based on this concentration, I can establish Kc, which is a formic acid concentration, and the carbon monoxide concentration, and water concentration. That will be x and 0.2 minus x and 0.2 minus x. And then here comes what I call the approximation. What approximation can I make? Approximation here. .2 minus x, when x is small, very small, it can be approximated to 0.2, right? So that's really the whole purpose for us to establish the new equilibrium constant, so that we can make this x value to be small. Okay, so now I'm going to use this approximation to finally get the simple equation, which is x 0.2 square. Okay, so therefore, what seems to be originally a kind of complicated equation now is x, and 0.2 minus x is same as a 0.2, so 0.2 square is, what was our Kc value? So we can go up there and look at it. Yeah, that's a 4.3 10 to the minus 5. So therefore, your x value here is 0.2 square divided by 4.3 10 to the minus 5. And then that value is about 9.3 10 to the minus 8 molar concentration. So we have justified that x is really, really small. Okay, so far we have a complete understanding about, we can answer any questions here, but let's go back to what was the question? Concentration of CO and concentration of H2. So the question was concentration of H2O, concentration of CO, which is 0.2 minus x. Right? And you have calculate the x values here is very small, so it's actually the answer is we don't need the whole of them. This happened to be. We can just using the fact that we have a better understanding about how to use the fact that Kc is really large. So 0.2 molar, 0.2 molar. That's, I mean, compared to 0.2, this number is really small. So actually, this is an answer. So in a way that if you do not just use any equations, just think about this way. When Kc value is here and the initial concentration was provided here, and then equilibrium heavily favor the products, and then at the end you will have this one is produced, almost complete conversion, right? So that's the idea. So answer for this concentration is now is 0.2 molar and 0.2 molar.